Welcome to the deep dive. So today we are tackling a truly monumental figure in modern mathematics, John Milnor. For anyone who might not know his name, you should think of him less as just a genius and more like an intellectual cartographer, someone who actually redrew the maps of mathematics.
That is the perfect way to frame it. I mean, when you look at Milnor's work, you see he wasn't just stuck in one specialty, he was building bridges. His insights they seamlessly connected topology, geometry, algebra, and, the whole wild world of dynamics. It's like he didn't even see the boundaries between disciplines.
And the timeline of his awards proves that, right? I mean, we're talking about a career that spans more than 6 decades. He gets the Fields Medal in 1962 for differential topology, and then almost 50 years later, the Abel Prize in 2011 for contributions across topology, geometry, and algebra. That's a whole career bookended by the 2 biggest prizes in math.
Yeah, and it's the style of his work that's so important to get. The sources we looked at really emphasize this. His legacy isn't just one big theorem, it's this unique approach. It's all about deep conceptual insights, really elegant proofs, and my favorite part, these pioneering counterexamples. They didn't just challenge assumptions, they sort of shattered them. They forced everyone to stop and recalibrate.
So our mission for this deep dive is to unpack that legacy for you.
Right.
We want to focus on the core conceptual breakthroughs he introduced. And I think we have to start right at the beginning with this truly shocking discovery he made back in 1956 that kind of redefined what a shape even is.
Absolutely. Let's start with section 1, the revolution of exotic structures.
Okay, so the moment you mention Milnor to a topologist, the first thing they say is exotic spheres. But for the rest of us, that just sounds, well, like a paradox.
Yeah.
How can a sphere, the most basic shape we can think of, be exotic?
It's a brilliant paradox, and it gets right to the heart of what geometry even means. So imagine a standard 7-dimensional sphere, a 7. Milnor discovered that there are other smooth structures on this sphere, and these structures are not smoothly equivalent to the standard one. But here's the key part. Topologically, they're exactly the same. They're homeomorphic.
So if you were to, stretch or bend them, they'd match the standard sphere perfectly. They have the same number of holes, all that stuff.
Precisely. From a continuous deformation standpoint, they are identical. But he showed they are not the same if you bring in the idea of smoothness. The ability to do calculus on them to measure curves and tangencies. They are not diffeomorphic. The geometric structure, how you define flatness at a microscopic level, is just fundamentally different.
Wow, that must have just rocked the entire field. Why was that so shocking? Did people just assume that if 2 things were topologically the same, they had to be smoothly the same too?
Exactly. Before 1956, that was the conventional wisdom, at least in higher dimensions. There was this comfortable idea that smoothness was just part of the shape. And Milnor comes along and says, no, smoothness is an added layer of structure. And you can have multiple incompatible layers on the exact same topological object. I mean, that just opened the door to this terrifying complexity in high dimensions.
It's almost like discovering 2 cities that look identical on a map, but when you try to drive through them, the road systems are completely different. You need a whole new set of rules.
That's a great analogy, because Milnor basically had to invent the rules. To navigate these new landscapes, he had to develop entirely new tools.
And one of those was something called microbundle theory.
Right. Microbundle theory was a new framework he came up with to handle fiber bundles, which are structures that describe how a small geometric space, the fiber, is attached to every point of a base space. The standard theory just wasn't flexible enough for these exotic things, so microbundles gave him the right structure to work with.
So he didn't just find a problem, he built the custom software to solve it.
That's his hallmark, really. And then he and Michel Crever co-developed the foundations of surgery theory. If microbundle theory was the software, surgery theory was the fundamental surgical tool.
Tell us a bit more about surgery theory. What was the goal there?
Well, the goal was classification. Surgery theory gives you this methodical, step-by-step way to transform one manifold into another. You perform surgeries, you cut out a piece and glue in a simpler one, and by doing this, you can classify high-dimensional manifolds. It became the essential toolkit.
And all of this came together in the Crever-Milnor theorem.
Yes. That was the crowning achievement. It successfully classified all the exotic smooth structures on spheres and dimensions greater than 4. Just think about that. He discovered this complete chaos, and then he and Crever mapped it all out and restored order. It was just a massive foundational achievement.
And that's a perfect transition, because his focus wasn't just on abstract classification. He was always creating tools for analysis. And we see that shift when he moves into geometry, focusing on the local behavior of shapes. especially where they sort of break.
Exactly. So this brings us to section 2, analyzing shapes and singularities. After classifying the big picture, he zooms in on the fine details, the wrinkles, the folds, the singularities.
For those of us who don't deal with this daily, what exactly is a singularity in this context?
Okay, so imagine a surface defined by an equation. Usually it's smooth, like a bowl. A singularity is a point where that breaks down. The surface isn't smooth anymore. It might have a sharp tip, or it might cross over itself. Milnor gave us the tools to understand these points.
And those tools are the Milnor fibration and the Milnor number. How do they work?
They're like a perfect mathematical microscope. Before him, understanding what was happening right at a singular point was really hard. The Milnor fibration is a special map, the Milnor map, that lets you look at the space right around the singularity, and it shows that even though the manifold is degenerate at that one point, the space around it actually fibers beautifully over a circle.
Wait, so he found a hidden regularity right near the point of collapse.
That's the insight. It proved that even with this local breakdown, the topology right around that point is highly organized. And then the Milnor number quantifies that complexity. It's an invariant, a number you can calculate that tells you exactly how wrinkled the singularity is. It became a foundational measure.
It's amazing how he could go from thinking about the global properties of a seven-dimensional sphere to the microscopic behavior of a single point.
And that vision just kept expanding. He took those insights from singularity theory and applied them in differential geometry, which led to the Milnor-Wood inequality.
Tell us about that. How does that connect to the bigger picture?
So this result is about something called foliations and flat bundles. Without getting too technical, the inequality basically puts a limit on how complex these structures can be on a surface. It gives you a boundary. What's crucial is that the techniques he used came from his mastery of analyzing these bad points, these singularities. It showed how a tool for one area could solve huge problems in another.
It seems like every time he defined a new geometric structure, he immediately had to develop the algebraic rules to describe it, which pushes us into pure algebra.
And this is section 3. Algebraic structures and K-theory. The transition from geometry to algebra is just seamless in his work because he was always hunting for the fundamental framework.
And the new language he gave us was Milnor K-theory. Why did we need a new K-theory? What was it solving?
Well, classical K-theory was great, but Milnor K-theory was this. Streamlined, purely algebraic structure. It captured certain aspects of geometry, especially relationships in field theory and number theory, with just incredible elegance. It defined a new algebraic relationship between fields.
So it became a cornerstone.
Absolutely. It was immediately central to algebraic geometry and number theory. It gave people a way to measure invariants that were just inaccessible before. It's pretty remarkable that a guy known for topology could invent something that anchors pure algebra.
But he wasn't just defining abstract stuff. He was also a master builder, giving mathematicians a practical way to create geometric objects. I'm talking about the plumbing construction.
The plumbing construction is one of the most just beautiful and practical ideas in manifold theory. If you think of a manifold as some complex building, Milnor gave us the blueprint.
So how does it work conceptually?
Imagine you take a bunch of simple tube-like pieces disk bundles over spheres, and you connect them by gluing their boundaries together in a really specific way. It's like using standard pipe fittings to build an incredibly complex, high-dimensional plumbing system. The technique lets you construct all sorts of things, like those exotic spheres or manifolds with very specific properties that would be impossible to define otherwise.
So it moves from an abstract proof to a concrete constructive method. It gives you the power to test theories by just building the object you need.
It's the practical side of his theoretical genius.
We've covered static ideas, classification, analysis, blueprints, but Milnor also dealt with motion and change, with chaos. His curiosity just drove him to study systems that evolve over time.
And this brings us to section 4, the dynamic world of change, which covers dynamical systems and group theory.
In this area, we find the Milnor-Thurston kneading theory. What does kneading refer to here?
The term kneading literally comes from the idea of stretching and folding dough. It's that classic visual for chaos. This theory was a huge advance for one-dimensional dynamical systems, like iterative maps. It gives you a way to quantify the complexity of these chaotic-seeming systems.
So it helps figure out how complex the outcome of all that stretching and folding is going to be.
Precisely. It connects the topology of the system, how it folds over itself, to its entropy, which is the mathematical measure of its chaotic information. It's a powerful bridge between the structure and the outcome.
Now, you mentioned earlier his career is defined by these groundbreaking counterexamples. The exotic sphere was the first one. What was the second major shockwave he sent out?
That would have to be the construction of isospectral non-isometric manifolds. This is one of those ideas that just breaks your brain in the best way. The concept is often summed up by the question, can you share the shape of a drum?
Right, I remember that analogy. It means if two drums sound exactly the same, if they have the same set of harmonic frequencies, then their shape must be identical.
That was the assumption in spectral geometry for decades. The spectrum of a manifold is related to its vibrations. But Milnor, in 1964, he proved that you can have two different geometric shapes, two manifolds that are isospectral, so they sound the same, but are not isometric. They are not geometrically identical.
That is a profound violation of intuition. So hearing the geometry doesn't actually tell you what it looks like.
Yeah.
That just shatters the idea that spectral data and geometric data determine each other.
It completely shattered that assumption. It confirmed that there's geometric information that is totally hidden from vibrational analysis. And that opened up this huge new area of research, trying to figure out what else you need to know to fully characterize a shape.
And finally, rounding this out, we have the Avark-Milnor lemma, which connects group behavior to the geometry of spaces.
Yeah, this lemma is so key in geometric group theory. It provides a really powerful bridge. It essentially says that if a group acts nicely on a metric space, then the growth rate of the group, how fast its elements multiply, is directly linked to the large-scale geometry of that space.
So if you can understand the algebra of the group, you can infer the geometry of the space and vice versa. It's like a dual lens.
Exactly. It's a deeply practical tool that lets group theorists use geometric intuition and geometers use algebraic tools.
So if we zoom out, we've covered four massive areas: topology, geometry, algebra, dynamics, and each one contains these foundational theorems that define their fields. His impact wasn't incremental, it was transformational.
The power of Milnor's legacy is really his ability to synthesize. He didn't just borrow tools, he created the bridges. He saw the underlying connections where other people just saw separate disciplines. A grand unifier.
Which brings us back to his style. Not just the results, but the clarity and elegance of it all. Deep insights, accessible proofs, and those powerful, boundary-pushing counterexamples.
And that accessibility is so well preserved in his books. His textbooks, like Topology from the Differentiable Viewpoint, they're still classics. They convey incredibly complex ideas with startling clarity. They're still the first books new mathematicians read.
It's a career that's gotten almost every high honor you can imagine. Beyond the fields in Abel, there's the National Medal of Science in '67, the Wolf Prize in '89, the Lomonosov Gold Medal as recently as 2020.
I mean, the evidence is just overwhelming. Our sources all confirm that Milnor's legacy is his ability to redefine these mathematical landscapes. It was the conceptual breakthrough, the discovery that smoothness isn't fixed, or that the spectrum doesn't tell you the whole shape, that opened up whole new fields for others to explore.
He taught us that what we thought was a perfect sphere might actually be something totally different under the surface, and that the sound of an object can mislead us about its shape.
Which really raises a powerful final question for you, the listener, to think about. Milnor's genius was in bridging these divides. Exotic spheres broke the boundary between topological and smooth. Isospectral manifolds broke the boundary between sound and shape.
So as you look at the academic or technical world you live in, where are the current comfortable boundaries between fields that are just ripe for a Milnor-style breakthrough? What fundamental assumption in your field, if you hit it with the right counterexample, might reveal a whole new dimension of complexity?
Yeah, think about what other fields, machine learning, complex systems, maybe even economic modeling, could benefit from his approach. You know, this interdisciplinary, counterexample-driven way of challenging what we all take for granted. That ability to see connections where others only see walls. That's John Milnor's true, enduring legacy.